Here is our latest CNC build. I apologize, I did not do a full build series on this one. I just didn't film as we were building, so I thought I would just go over all the specifics in detail on this guy as it's currently built. We have it over here doing a bit of work on it and just some maintenance, so I thought I would kind of open it up and show you what's going on and show you some of the changes we made over our previous build. So we did a full build series on a table style machine that we have been using extensively for the last year, and this is our newest addition. So this guy looks like an overly complicated vending machine, but it is a simple 3-axis CNC. It's fully contained, and it manufactures a specific product for us that we're manufacturing in large quantities that actually required us to build a specific machine for that operation.
This machine was built in a bit of a hurry because we needed something right away, and the unfortunate side of that is that we did not record the actual building process, but I still wanted to walk you through this little guy. I will be referencing our last build throughout this video. We did a complete build series on that last machine, so it is worth a watch to understand some of what's going on here. It was built to produce a product that we sell in enough quantities to merit a dedicated machine, so much of the design considerations were focused around that intention. The overall build methodology is very similar, with some amendments based on its purpose, as well as lessons learned from that last project. Those lessons included structural changes that should be incorporated into future builds, and improved considerations for noise suppression, debris management, maintenance, and efficiency. I know that sounds like a bunch of corporate buzzwords, but because we build and use these machines every day in an industrial setting, any faults in the design fall right back on us, so we really do care about them. That said, the result is a machine with a 300 by 400 by 150 millimeter working platform, that's XYZ, in a fully contained design. It features the same Meso touchscreen controller as the previous build, a full air system, an auto lubrication system, standalone debris collection, and vastly improved maintenance considerations.
Up front, from the bottom up, we have our debris collection door. I'll show you underneath there. We have our door to load stock and monitor the machine. That touchscreen display, which is the same as we have previously used. We have a nice little tower light on this one. Gauges for monitoring various systems. We have an hour meter, which ironically has failed, and that's part of the service we're doing on it today. Power switch and a button to cycle our air system. We also have this little remote blower here, which is a handy little feature just for blowing off things as they go out of the machine. Inside and behind this door, we have some pop latches, a fully gasketed door, and inside you can see this perimeter lighting, makes it nice and bright in here. And you'll notice that we did something totally different with the overall design of this machine. The previous build was a gantry style machine, so the X and Y and Z axis all travel over a static work surface. This one we did it differently. So to achieve our containment goals, it worked a lot better for us if we did not have a moving gantry. So our Y-axis travels laterally here, and our table moves as the X-axis. So it's a bit of a hybrid design, and that was just a necessity based on what we were trying to achieve with it. It also allowed us to try something a little bit different. So you can see how by this part not moving, we can seal all this up onto our side panels, and we can contain all that debris and channel it to where we want it to go. We have these sloping side plates. We have 2 layers of them. So we have this upper layer in here, and we have a whole second layer underneath that funnels everything down into a debris collection bin. And that has allowed us not to need a dedicated dust collection system hooked up to this machine. We are reaching the capacity of our dust collection. So any machine that can run without it is going to be of huge benefit to us. And this one has worked great without. You'll notice that some of the design elements of this machine are very similar to the previous build, with some changes made to accommodate this new design architecture that we've decided to use. And we did learn some lessons from that previous machine about where we needed to add steel, change steel, and just general things that needed to be modified if we were going to build something similar. So we've incorporated that into this machine to increase the overall performance and facilitate some of the construction. We had positive and negative results in that endeavor, and we'll go through some of those. We have a 2.2 kilowatt spindle underneath this assembly here. We'll pull this guy off at some point, and I will show you what it looks like under there. And then our table, it's an all aluminum fixturing table because, as I mentioned, it does one product in a single stock size. We just set this up to accommodate that and just set and forget. We're not going to put a vise or anything on here.
Next, we're going to pop those side panels off to take a looky-loo inside.
With the side panel off, you get your first peek inside the machine and the structure itself, and it can only really be described in one way, and that is Unibody. And I know that may make some people shudder, and the general concept has negative connotations, but let me explain. The way we just chose to build this was not to segregate the various systems on the machine. So we don't have a structure, enclosures, a stand, and a containment. We chose to give everything two purposes. So we still have our general machine structure, which is as beefy as anything we've ever built, but every other system, including dust management and the electrical box and the stand, all are part of the same collection of plates and contribute to the overall rigidity of the machine. So what we have developed is a system that's not only easier to put together, but we get a lot of bang for our buck as far as the amount of steel on this machine and the overall strength of all these components, because none of it is being wasted on a single purpose. And because there's so many different systems on this machine, we get a lot of plates working in many different directions to form the greater structure. Everything aluminum on the machine, those are independent components, including the sides and top, and we chose to make those removable to achieve our maintenance goals. So that was the only reason they weren't included in that general design philosophy, and I think that's for the better. With the side panels off, you can see just how easy it is to perform maintenance and repairs on this guy. We wanted to keep everything as accessible as possible when those covers are off. So it was all designed around managing our wires such that we can get to them, our air lines, all our systems. I wanted bolts to be accessible, wires to be right there, and didn't want too many buried pieces of equipment anywhere. So that goes for everything inside here, to the back as well, where we have all our electronics easily accessible for diagnostics and replacement. All the belts of the machine can be accessed by removing these two panels, as well as most of our bearings and various sensors and regulators. They're all right there, so even this hour meter that I need to replace, I can take that side panel off, I can pop that guy out, no problem. So underneath here, behind our debris collection tank, we have all the reservoirs for the various systems on the machine. We have an air accumulator for our air system, followed by an auto oiler that supplies all the oil to the various air systems on this machine. We have a coolant reservoir and pump for the spindle coolant, and a pump and reservoir assembly for the machine oiler. All three movements are driven with ball screws, and the motion is communicated through these belt drives. So all three of the axes have that one up there. And then we have one back here. We've currently removed it to do some work on the machine, but there was a belt drive for the X-axis back in the electronics bay. And the reason we went with the belt drives was twofold. Number one, reduce the overall size of the machine. So with these mounted reverse and parallel to the axis itself, it allowed us to make the machine narrower and a little bit shorter. Not the main reason we did it. The main reason was to get some tunability out of our drive ratio. We were trying to achieve some fairly high travel speeds with this guy. So we were running a 2-to-1 overdrive on all the belts. That is 2 turns on the ball screw, 1 turn on the stepper motor. And that was to achieve those high travel speeds while still operating in the ideal RPM curve of the stepper motor. We've since eliminated that and gone to a 1-to-1 on all three because we were having some problems and we couldn't achieve those idealistic speeds anyway, so we just decided to simplify it and go to a 1-to-1. I'm running these smaller pulleys because that is all I had, but I do want larger pulleys just to reduce some tension on the belt so it's not being pulled as hard. Mostly because we determined that the belt is contributing to surface finish issues on our pieces. It does have, despite these slightly wider belts that we decided to go with, they have some spring and some bounce in them. And under rapid directional changes, that was translating to marks in our surfaces. So in general, I'm probably not going to use them again. If we were able to achieve those travel speeds, and the 2-to-1 worked. I might compromise, but not a big fan so far. So underneath that Z-axis plate here, we have our 2.2 kilowatt spindle mounting bracket and this little air blower, and that's just plumbed back to the air solenoids to purge our tool. We also have these 2 cylinders on either side of the spindle. They are anchoring the Z-axis plate to the Y-axis assembly. And they are to assist with the lifting action of the Z-axis assembly. We found on a previous machine that our travel speeds were being limited by the acceleration rate of the Z-axis assembly, just because it's jacking up all that weight every time it's got to make a Z move. And in our case, we're talking about 50 pounds of material here between the spindle and the plates. We beefed up this back plate on the previous machine that was a 1/4 inch plate. We've since upgraded that to a 1/2 inch plate to increase our rigidity. So we're dealing with quite a bit of weight. We thought we'd add these cylinders to either side. They're just 2 16 millimeter diameter cylinders, and we have a positive air charge fixed onto the pull side of the cylinder, so they're constantly pulling everything up. They are regulated to 30 pounds of pressure, which produces 14 pounds of lift on either side. And on the lateral plane here, they are basically center of mass, so they're in a good location for lifting, and they offset about 50% of the overall weight. We found some of the weight on the tool was good. If we took away too much, it was decreasing our finish quality, so we left a little bit of weight just to keep that tool down. So these guys, as mentioned, have a positive air charge fixed to the pull side of the cylinder. And then on top, where they're anchored, we do have an air line, which would be the other side of this double acting cylinder. It's no longer a double acting cylinder, so this has just become an oil drain to purge the oil that enters the cylinder, because we have a dedicated oiler up there. So you can see that copper line right up there. We drilled a hole in the backside of both of these double acting cylinders and tied them into our oiling system to ensure that they get adequate oil. And so far those have worked really good. Noticed a substantial increase in our Z-axis acceleration rates, and beyond that we have increased the overall efficiency of the machine. That Z-axis motor is not doing nearly as much work to provide those lifting actions. So all in all, pretty happy with those. I will add those to all our future machines so long as they have an air system. The table down here is a 1/2 inch aluminum plate with end stops built into it and an air vise assembly. We didn't want to mess around with a vise and tools to simply switch out our stock, so we thought we'd just throw it in here. Our zeros don't change. We throw a valve for this air vise and it clamps it in place with about 300 pounds of pressure. We never have to worry about it. So the air vise is actuated by a valve that is housed inside the machine. I wanted it inside the machine just so it didn't get bumped when it's running. So this opens and closes that air vise, and all that air travels through a couple throttling valves. So we have 2 little flow regulators here to control the opening and closing speed of the vise. I didn't want to hammer it against my stock, so those are there just to control that extension and retract rate. And so far I've had no problems with that system. We have an indicator on the outside of the machine, so it is tied into our air gauge here. So this second value, the primary value, is going to be machine air, and secondary value is going to be vise air. So as long as we have an air charge to that vise, we know that we have everything clamped in place and we don't have to worry about it. If that number is reading 0, it is not clamped. So on the back side of the machine, we have our electronics bay. So we wanted the electronics to be much more accessible on this machine, so we decided to mount them somewhere where we could get to them. And this seemed like kind of the best option. So back here, in this recessed cavity, we have our VFD, our stepper motor drivers, that Y-axis stepper motor, the power supplies, and a bunch of the other equipment for the electronics on this guy. We have some relays connected back to the controller for various AC systems, and our full solenoid block for the air system. We have the X-axis motor poking through there, and the X-axis ball screw. We're doing some work, which is why the belt drive system is gone, but otherwise there would be a belt drive there as well. And then on the door, it's all air cooled to keep this bay nice and temperature controlled, with the lower fan also being the radiator for the spindle cooling. So air comes in through the top, moves through this whole bay, and gets pushed out through the radiator. And then that coolant is fed back into the reservoir where it's eventually pumped up to the spindle. So in the equipment down here, we've got a breaker for internal power, some terminal blocks distributing that AC power. We have a 24 volt power supply, which powers the controller and the solenoids and some of the relays. A terminal block for distribution of the DC power. We have this relay timer, which cycles one of the solenoid valves over here, and that's for our air blowers. And then we have a 6-pot relay block that's a Meso supplied relay system, which just ties back to the controller, gives the controller the means to run some of the AC equipment like the auto oiling pump. So as part of the coolant system for the spindle, you saw that radiator mounted into the door of the electronics bay. That feeds from the spindle directly into this coolant reservoir, where it feeds this 24 volt circulation pump that pumps cold coolant directly back into the spindle. The auto oiler on this guy, this is our first crack at this. This is a 220 volt pump. It produces about 240 pounds per square inch of pressure. It has a 2-liter reservoir and a low oil indicator. We're powering it with the controller. The controller has a cycle sequence for an auto oiler. So when it runs, it turns this guy on and it supplies pressurized oil through a series of lines to 2 separate distribution manifolds that we have. One of them is up here. So this is our first assembly, and basically the way this works is it receives supply oil from this line here. It charges all these individual chambers all the way across. We have 8 of them up here, and once pressure is relieved from the system, there are spring-loaded pistons in here that push a specified amount of oil up through our oiling lines to our various oiling points. That amount is 0.3 milliliters. So every time it cycles, it's going to send 0.3 milliliters of oil to those various points. Up here, it's lubricating all our bearings, drive screws, and lift cylinders for both the Y-axis and Z-axis assembly. And then we have a separate one down here. You can kind of see it poking out down there. And that supplies the bearings and drive screw for the table assembly. So it seemed easier to mount these manifolds to the moving assemblies rather than keep them static and have to run soft lines to our various locations. And it's worked pretty good. I'm pretty impressed with these. They've saved us a ton of maintenance. We don't have to grease these bearings and stuff all the time. The rails stay cleaner, and I assume the components are all going to last a lot longer. This 2-liter reservoir does about 300 hours before it needs to be topped off. And when it's low, it has a float in there that will indicate to us on the controller screen that it is time to top off that oil. Before the air enters the accumulator and the auto oiler and feeds all of the air systems on the machine, it first comes into this little splitter. We have an air pressure gauge here, which is tied back to the gauge on the front of the machine and just indicates that we have air pressure. And then this orange line here feeds the air blower assembly, just the manual nozzle on the outside of the machine that we just use for cleanup. But after that, it goes into an accumulator, into the auto oiler, and then up to a distribution manifold and various regulators. One of those regulators is the regulator for the airlift assist cylinders, which I explained earlier. And back here we have our air solenoids. So I have a manifold of 4. I'm only using 2 right now. They control the purges on the machine and the blow off for the tool setter. And eventually the other tool will be used for an automatic tool changer. So I've left those there. On top we have a pressure switch. So this ensures that there's pressure in the entire air system on the machine that is tied back to the controller. If the air pressure drops below a certain amount at any point, it shuts down the machine because it is sort of a critical system. So that's tied into an alarm input on the controller, and it will shut the whole system down if there's a problem. Our air blower here is just to keep the tool clean, so we have a magnetic base on it with a throttle valve. It's part of a greater air system, which includes air blowers on the rear of the machine, and on the front of the machine. So these air blowers are designed to keep the tool clean. Obviously this guy up here. These ones back here are designed to keep the bellows clean. So we're trying to keep debris from building up in these bellows. There's a lot of channels there that seem to collect and hold material. So they are on a cycle rate and designed and aimed just to purge those out on a specific increment to make sure that they stay clear, so we're not jamming up in here when the table travels to either extreme. They stay nice and clear, and it moves all that material down to our refuse container underneath.
So there you go, there's the whole machine in a nutshell. We are really happy with the overall design. I hope you can appreciate that we did something a little bit different. We traded a lot of versatility for some increased efficiency in our operation, and we definitely hit the nail on the head with that second one. It is indescribably better for pumping out these products than that previous machine. The fixturing's great, the dust containment, the debris management, and even the noise suppression. It is considerably quieter than that other guy, and when we have a fleet of these, that is really going to start to count. There are some quirks with the design that'll be worked out over the next builds. I definitely could have improved some of my margins. It didn't need to be quite so small. We're cutting it a little tight on some areas. I'd like to put bellows over the y-axis rails, and the whole machine just ended up being too small for that, and that's just one example of me being a little optimistic with the overall size. Even access to the machine is a little restricted through that tiny door. We only have to load it once every couple hours, so it's not a big deal. I would still prefer an improved consideration for access inside, just to make it a little less awkward and improve the usability. But rest assured, in the next build, there will be a lot of carryover, and the new machine will look very similar. If you have any questions, feel free to reach out. We are on a constant endeavor to reinvent these machines and fill our operational need, so there will always be more content and new lessons learned, so please subscribe if you'd like to see more.